Hello dear friends and welcome. I am so glad you have decided to join me here today. Before we begin, I want you to find a comfortable position. Relax your shoulders, take a deep breath and let the noise of the day slowly fade away. Let us start with an image. I would like you to close your eyes for a moment. Imagine that you are standing in the middle of a vast open field. It is late at night. The air is cool and crisp against your skin. Above you, the sky is not just a ceiling. It is a deep, endless ocean of velvet black. When we look up at this night sky, our human brains naturally try to find patterns. We connect with the bright dots of the stars to draw pictures. We see hunters' bears and scales. We name them constellations. We like to believe that the universe is a perfect, orderly machine like a giant clock where every gear turns exactly as it should. We find comfort in the idea of structure. We want to believe that everything stays in its lane circling the sun in perfect predictable loops year after year, century after century. But my friends, the universe is not quite as tidy as a clock. Beneath that calm blanket of stars, there is a beautiful, silent chaos. The solar system is less like a perfectly organized highway and more like a busy, dusty room. Between the planets, there are millions of leftovers from the time when our world was born. There are rocks, pebbles, dust, and mountains of ice floating in the dark. Most of the time, they are invisible to us. They drift quietly in the shadows far away from the warmth of the sun. They are the silent wanderers of the void. Usually these wanderers follow the rules. They belong to our family. They were born from the same cloud of gas and dust that created the Earth and Mars and Jupiter. They are our distant cousins, bound to the sun by gravity just like we are. They stay within the fence of our solar system. However, every once in a great while, the universe decides to surprise us. It reminds us that our solar system is not an island. We are part of a much larger neighborhood, a galaxy filled with drifting mysteries. And this brings us to why we are gathered here today. Something truly remarkable has happened. In just the last 24 hours, the steady rhythm of the astronomical community skipped a beat. The whispers started in observatories and quickly spread across the globe from computer screen to computer screen. A telescope known as ATLAS has spotted something new. Now let me explain ATLAS briefly. It stands for the Asteroid Terrestrial Impact Last Alert System. It is a network of robot telescopes in Hawaii and other places scanning the sky every night. Its job is usually to act as a guard dog watching for space rocks that might come too close to Earth. It looks for things that move against the background of the fixed stars. Yesterday it found a faint point of light. At first glance it looked like just another asteroid, a piece of rubble tumbling through the dark. But when the astronomers looked at the numbers, when they looked at the math describing its path, they realized something was different. This object was not moving like a normal asteroid of the mountain. It was moving too fast. And more importantly, its angle was wrong. Most things in our solar system orbit on a flat plane like plates on a dinner table. This object was diving down from above, cutting through the table at a steep angle. They have given it a preliminary label that sounds technical but carries a huge weight of history. They are calling it 3I/Atlas. The 3 is the most important part of that name. It stands for the number 3. The letter I stands for interstellar. This means between the stars. This object, this traveller, is not from here. It was not born in our solar system. It did not form from our sun's dust. It is a visitor from deep space, a guest from another star system entirely. To understand how special this is, we have to look back. In all of human history, as long as we have been watching the skies, we have only ever confirmed 2 other visitors like this. The first was in the year 2017. You might remember the name Oumuamua. It was a long, strange cigar-shaped rock that tumbled past us before we barely knew it was there. It was a scout, a mysterious messenger that left us with more questions than answers. The second visitor came 2 years later in the year 2019. It was called Borisov. That one was clearly a comet trailing gas and dust, looking familiar but coming from an alien home. And then silence. For 5 years, the skies were quiet. We watched and we waited, wondering when the next traveller would arrive. Yesterday, the wait ended. 3I/Atlas is the third confirmed interstellar object in history. Just think about the journey it has taken. This object has been travelling through the freezing void between stars for perhaps millions of years. It has drifted through total darkness far from any sun. It has passed through the emptiness where there is no sound, no heat, and no light. It has been flying alone for eons. And now, purely by chance, its path has crossed with ours. It has entered the light of our sun. It is waking up. As the sun's heat touches its surface for the first time in ages, we are waiting to see what happens. Will it crumble? Will it sprout a tail of gas like a comet, or is it a solid rock, a silent monolith like Oumuamua? The initial reports from the last 24 hours suggest it is small, perhaps only a few hundred meters across. To the naked eye it is invisible. Even to most telescopes it is just a speck. But to us it is a treasure chest. It contains the chemistry of a distant star system. It carries the story of a place we will never visit, a place light years away. This discovery shakes us out of our routine. It is a gentle reminder that the chaos of space is actually full of gifts. We often think of space as empty, but it is actually full of traffic. It is just that the roads are very, very wide. So as you sit here with me, imagine that small lonely rock. It is currently racing through our solar system at incredible speeds, tens of thousands of kilometers per hour. It does not care about our politics, our borders, or our daily worries. It is simply passing through a traveller on an endless voyage. We are lucky to be awake right now to witness it. We are the generation that gets to see the third visitor. In the coming days, telescopes all over the Earth and even those in space will turn their glass eyes toward this new guest. We are going to learn its shape, its colour, and perhaps what it is made of. But for now, in these first few hours of discovery, we can just appreciate the mystery. There is something beautiful about the unknown, isn't there? It reminds us that there is still so much left to discover. The dark is not empty, it is full of potential. So take another deep breath. Let the wonder of that thought settle in your mind. A visitor is here. The universe has knocked on our door once again. In the quiet, cold nights of the Soviet observatory away from the political noise of the world, two scientists named Medvedev and Pavlov were looking for something others had missed. They were not looking for a giant explosion or a sudden crash of stars. They were looking for a pattern. To understand what they found, we must first imagine the universe as it usually appears to astronomers. The universe is generally a chaotic, noisy place. It is full of fire destruction and random energy. Stars burn unevenly, dust clouds swirl without direction, gravity pulls things apart in violent ways. If the universe were a room, it would be a crowded party where everyone is shouting at once, glasses are breaking and the music is unpredictable. But when Medvedev and Pavlov pointed their instruments at CTA 102, the shouting stopped. In the middle of that chaotic party, they heard a single steady sound. It was distinct, calm, and terrifyingly precise. They had discovered the cosmic heartbeat. Imagine a simple wooden metronome. You place it on a table in the middle of a storm. Thunder crashes outside, the wind howls, and rain hits the window in random bursts. But inside, the metronome moves back and forth. Tick, tock, tick, tock. It does not care about the storm. It keeps its own perfect time. This is exactly what CTA 102 looked like to the Russian scientists. Amidst the randomness of space, this object was keeping time. Medvedev and Pavlov began to record the data, translating the radio waves into charts on paper. What they saw on those sheets of paper changed everything they thought they knew about natural space objects. The data showed two distinct rhythms working together like a complex piece of music. The 4-hour cycle, the shift in position. The first rhythm they noticed was a slow, steady swaying motion. The data indicated that the source of the radio waves, the center of this mysterious object, was shifting its position. This was not a random wobble. In nature, when a planet or a star wobbles, it is usually because it is dying, or being pulled by the gravity of something larger. Those natural wobbles are messy, but this was different. Every 4 hours exactly, the signal would complete a full cycle of movement. Think of it like a giant pendulum swinging in the dark. It swings all the way to the left, pauses for a microsecond, and swings all the way to the right. It takes exactly 4 hours to return to where it started. It never sped up and it never slowed down. Medvedev watched the clock on the wall. At 12 o'clock the cycle began. At 4 o'clock the cycle completed and started again. At 8 o'clock it happened again. It was hypnotic. Nature rarely produces integers, whole round numbers that are this perfect. A natural orbit might take 4 hours and 3 minutes and 12 seconds, but this appeared to be exactly 4 hours. It felt intentional. It felt like a machine that had been programmed to sweep an area like a radar dish, turning in a circle, scanning the sky, and see with perfect regularity. The 2-hour cycle, the breath of light. If the 4-hour movement was the body of the machine swaying, the second discovery was its pulse. While the object moved every 4 hours, its brightness changed every 2 hours. Pavlov focused on the intensity of the radio waves, how loud or bright the object was. He found that the energy coming from CTA 102 was pulsing. Imagine a lighthouse standing on the edge of the cosmos. The light does not just stay on, it rotates. As the beam hits you, it becomes blindingly bright. Then as it turns away, it dims. Then it comes back around. Bright, dim, bright, dim. This happened with a 2-hour frequency. It was a soothing, rhythmic pattern. The object seemed to be breathing. One breath in the light grows stronger. One breath out the light fades softly. When the scientists laid the two charts over each other, the picture became even more beautiful and more impossible. You had the 4-hour swaying motion, and inside of that you had the 2-hour pulsing light. It was a perfect synchronization. For every one time the object swayed back and forth, it pulsed exactly twice. Sway, pulse, pulse, sway. It was a polyrhythm, like a drummer playing a beat with one hand and a different beat with the other, yet staying in perfect harmony. The implication of order. For Medvedev and Pavlov, the feeling of looking at this data was not just scientific curiosity, it was a profound sense of awe. In the cold observatory surrounded by silence, they realized they were looking at order in a universe of chaos. Gas clouds do not keep time. Black holes do not act like metronomes. Exploding stars do not breathe in and out every 2 hours. The scientists had to ask themselves the difficult question: how could a ball of gas or a rock create such a specific schedule? The answer that lingered in the silent room was that it couldn't. To their eyes, this looked like a beacon. It looked like a transmission. If you wanted to get the attention of someone across the galaxy, you would not send a complex message right away. You would send a rhythm. You would send something so artificial, so structured, and so repetitive that anyone watching would say, nature did not make that. The cosmic heartbeat of CTA 102 was exactly that. It was a signal fire in the dark. The 4-hour shift and the 2-hour pulse were not just random data points. They were the heartbeat of a machine pumping energy out into the galaxy with the steady, calming reliability of a clock. As the sun began to rise over the Soviet Union, ending their shift, the two scientists looked at their charts one last time. The lines on the paper went up and down, perfectly evenly. It looked less like a star map and more like an electrocardiogram, the medical chart of a beating heart. They had found the pulse. Now they had to figure out what was alive at the other end. When we look up at the night sky and see a comet, we usually see a beautiful glowing smudge with a long, elegant tail. It looks peaceful. It looks like a brushstroke of white paint against the black canvas of space. For centuries, humans viewed them as omens or spiritual messengers because of this ethereal beauty. But the reality of a comet is not beautiful in the traditional sense. It is violent, dirty, and incredibly destructive. In the middle of the 20th century, an astronomer named Fred Whipple coined a term that changed everything. He called comets dirty snowballs. This is the most accurate description we have, though some modern scientists prefer icy dirt balls. Imagine a giant mountain floating in space, but instead of solid rock, it is made of a loose mixture of frozen water, frozen gases like ammonia and methane, and a whole lot of black ancient dust. It is not a solid, sturdy object. It is more like the dirty pile of snow left on the side of the road after a winter storm, crusty, dark, and fragile. When these dirty snowballs stay far away from the sun in the deep freeze of the outer solar system, they are quiet. They are dead rocks. But as soon as they fall toward the inner solar system, the heat of the sun begins to attack them. This is where the chaos begins, and this is the standard behavior we expect from any visitor from the deep cold. As a comet gets closer to the warmth, the ice on its surface does not melt into water. In the vacuum of space, it skips the liquid phase entirely and turns straight into gas. This process is violent. It causes the surface of the comet to crack and explode. Jets of gas scream out from the interior, blasting dust and rocks hundreds of miles into space. This is what creates the coma, the fuzzy cloud around the comet, and the tail that flows behind it. We have seen this up close, and it's a scene of total disorder. Take the most famous example in history, Halley's Comet. When the European spacecraft Giotto flew past Halley in 1986, it did not find a shiny white ball. It found a pitch-black potato. The surface was darker than coal, it was lumpy and scarred, and it was active. The spacecraft saw massive jets of gas erupting from the surface like geysers on Earth, but much more powerful. These jets were not uniform, they were bursting out from random weak spots on the comet's crust. Even more revealing was the mission to Comet 67P by the Rosetta spacecraft. This mission gave us the most detailed look at a comet in history, and it confirmed that comets are the definition of chaos. Comet 67P looked like a giant rubber duck, two rocks smashed together in a slow-motion car crash billions of years ago. The surface of 67P was a nightmare of jagged cliffs, deep pits, and rolling boulders. As Rosetta orbited the comet, it watched the object fall apart in real time. As the comet warmed up, cliffs collapsed. Landslides buried confused regions of the surface. Huge cracks opened up. The gas jets were so strong that they actually pushed the comet around. This is a crucial point. Comets do not move in perfect lines. Because they are spewing gas out of random holes, they act like a deflating balloon flying around a room. The gas shoots one way and the comet gets pushed the other way. This makes their paths hard to predict with total perfection. They wobble, they tumble, they are volatile living things that react dramatically to their environment. This is what nature looks like. Nature is rough, nature is eroding, nature is messy. Now we turn our eyes to 3I Atlas. If 3I Atlas were a natural object, a driven-out comet from another star system, it should have followed these same rules. It had travelled for millions of years through the absolute zero of deep space. As it plunged toward our sun, it was exposed to temperatures that should have boiled its surface instantly. Astronomers waited for the show. They trained their telescopes on the object, waiting for the dirty snowball to wake up. They waited for the ice to sublime into gas. They waited for the fuzzy coma to appear. They waited for the chaos. But nothing happened. 3I Atlas did not behave like a dirty snowball. It behaved like a stone, or more unsettlingly, it behaved like a machine. First, there was the visual appearance. Throughout its entire approach, even when it was close enough to the sun that water ice should have been screaming into space, the object remained a single sharp point of light. There was no fuzziness. There was no cloud of gas. There was no tail. This suggests that the object was either completely devoid of ice, which is incredibly rare for a small object drifting in interstellar space, or its surface was made of something that does not react to heat in the way natural materials do. It was clean. Then there was the movement. This is where the contrast becomes most striking. Remember that normal comets wobble. The gas jets act like unpredictable thrusters, pushing them slightly off their gravity-predicted path. We call these non-gravitational forces. 3I Atlas showed a terrifying level of precision. It did not wobble. It did not tumble in a chaotic way. It cut through the solar system with the smoothness of a knife cutting through still water. Its path was determined almost entirely by gravity, yet it possessed a strange energy that didn't fit the profile of a rock. When we look at a normal comet like 67P, we see a struggle. We see an object fighting against the heat, breaking apart, shedding its skin and reacting violently to the stars. It feels organic in its destruction. 3I Atlas felt sterile. It absorbed the heat without complaint. It did not shed mass. It did not crumble. It maintained a structural integrity that is hard to explain for a natural object under such stress. If you throw a snowball into a furnace, it melts and hisses. If you throw a ball of steel into a furnace, it just gets hot and keeps moving. 3I Atlas acted like the steel. This lack of mess is what disturbed the data analysts. In the natural universe, especially on the scale of asteroids and comets, things are rarely perfect. Orbits have slight jitters, surfaces are rough and pitted, rotation is tumbling and uneven. 3I Atlas possessed a symmetry in its data that felt artificial. It was too quiet. The contrast is stark. On one side, we have the history of astronomy filled with crumbling outgassing, tumbling rocks that leave trails of dust across the sky. On the other side, we have this interloper, silent, compact, incredibly solid, and moving with a purpose that defies the chaotic nature of a dirty snowball. It was not behaving like a visitor that was reacting to our sun. It was behaving like a visitor that was ignoring it. The silence of 3I Atlas was louder than the explosions of Halley. It forced us to ask a question that science is often afraid to touch. If it is not a dirty snowball, and it is not a crumbling rock, then what is it? Nature makes mistakes. Nature makes rough edges. 3I Atlas had none. The data does not lie, but it does refuse to fit into the comfortable boxes we have built for it. When we strip away the noise and the background static of the cosmos, we are left with a single undeniable fact. The object is adhering to a strict, unyielding mathematical ratio of 2:1. In the chaotic language of the universe, this is not just a sentence, it is a shout. To understand why this is so disturbing, we have to look at how nature usually behaves. Nature is messy. Nature is rough around the edges. When an asteroid tumbles through the vacuum, it does so clumsily. It is a jagged rock pulled this way and that by gravity spinning on uneven axes. If you were to graph the light reflecting off a standard asteroid, the resulting line would look like a jagged mountain range, unpredictable, chaotic, and without a clear rhythm. It spins a little faster here, slows down there, and wobbles like a dying top. But this object is different. The data reveals a perfect synchronization between its rotation period and its fluctuation in brightness. For exactly every 2 rotations of the body, there is precisely 1 cycle of peak luminosity. It is not approximately 2 to 1, it is not 2.01, it is an integer. It is exact. In the world of physics and astronomy, we call this a harmonic. Harmonics are incredibly rare in natural macroscopic systems. You might find ratios like this in the orbital resonance of moons, like the moons of Jupiter dancing in time with one another. But those resonances are born from gravity smoothing things out over billions of years. They are slow grinding adjustments. To see a single isolated object displaying such a locked high-frequency internal harmonic is almost unheard of. This brings us to the distinction between natural formation and engineering. Think about a forest. The trees are scattered randomly. The branches grow toward the light in twisting unique shapes. That is nature. Now think about a quartz watch or a car engine. In an engine, the gears turn in precise ratios. If one gear turns twice, the other turns once. This is not an accident of gravity. It is the result of design. It is the fingerprint of intent. Engineers love harmonics because they represent efficiency, order, and control. Nature, on the other hand, favors entropy, the gradual decline into disorder. When we see a perfect 2-to-1 ratio pulsing from the darkness of deep space, we are forced to ask a difficult question. Are we looking at a rock or are we looking at a clock? If this were merely a scientific anomaly, one would expect the astronomical community to be buzzing with excitement. Papers would be published, telescopes would be redirected, the grand observatories of the world would be fighting for a glimpse of this impossible dancer. Instead, we have silence. This is the most unnerving aspect of the entire phenomenon. We live in the golden age of observation. The James Webb Space Telescope hangs in the cold dark, capable of peering back to the dawn of time. The massive fast radio telescope in China, the Sky Eye, listens with an ear so sensitive it can hear the whispers of dying stars. The European Space Agency, NASA, the CNSA, they all possess the instruments necessary to confirm what the amateur data is suggesting. Yet there is no press conference, there is no picture of the day featuring the object. When independent astronomers attempt to access the raw data logs from these major observatories regarding this specific sector of the sky, they often encounter corrupted files or maintenance gaps. It is a bureaucratic wall of silence. It feels less like ignorance and more like containment. Why would they stay silent? Perhaps it is fear. Science is built on the foundation of understanding the rules. When something comes along that breaks those rules, it is frightening. If this object is indeed artificial, if that 2-to-1 harmonic is a beacon or a byproduct of a propulsion system, then the history of humanity changes overnight. We are no longer the only ones playing with fire, or perhaps the silence is an answer in itself. If you were a government agency and you detected a potential signal, a techno-signature, your first instinct would not be to tweet about it. Your first instinct would be to assess the threat. You would want to know what it is, where it is going, and what it wants long before you tell the public. The silence suggests that they have already looked. It suggests that they have analysed the harmonic ratio, realised that rocks do not behave like metronomes, and made the executive decision to close the blinds. We must also consider the nature of the ratio as a form of communication. Mathematics is often called the universal language. A prime number sequence or a perfect geometric ratio is distinct from the background noise of hydrogen radiation. If you wanted to signal your presence to another intelligent species, you would not send a complex poem. You would send something that cannot be mistaken for nature. You would send a pattern. A simple perfect harmonic is a lighthouse beam cutting through the fog. It says, I am ordered, I am consistent, I am here. The universe is vast, and for the most part it is indifferent to us. It crushes stars and swallows light without a second thought. But this feels personal. The precision of the signal feels like a direct gaze. It is the difference between hearing the wind howl through a canyon and hearing a clear rhythmic tapping on your window pane at night. One is weather, the other is a visitor. As we stare up at that point in the sky, knowing that the light curve is pulsing with the steady mechanical rhythm of a heartbeat, the silence from NASA and the CNSA becomes deafening. It validates our suspicion. They are not ignoring it because it is nothing. They are ignoring it because it is everything. They know that the whispers are not random. They know that the harmonics are not a fluke. They are waiting just like us to see what happens when the count reaches 0, or perhaps they are terrified because they have realised that the signal was not meant for us at all, but for something else entirely, something that is waiting in the dark, listening to the same 2-to-1 rhythm and preparing to answer. The math is perfect, the silence is heavy, and somewhere in the distance the gears of the cosmos are turning with a precision that suggests a hand is on the wheel. The engineer's blueprint. To truly understand the mystery of Oumuamua, we must stop thinking like astronomers and start thinking like engineers. An astronomer looks at the sky and asks, what is nature capable of making? But an engineer looks at a problem and asks, how would I build a machine to solve this? Let us perform a thought experiment. Imagine that humanity has survived for another 500 years. We have become an advanced technological civilization. We decide to send a probe to a distant star system, perhaps to look for life or to map the galaxy. The journey will take thousands of years and the destination is light years away. How do we design this ship? What does the engineer's blueprint look like? When we analyse the design requirements for such a journey, we realise that the strange features of Oumuamua, the shape, the movement, and the lack of dust might not be accidents. They might be solutions. The problem of propulsion. Why the shape matters. The first problem an engineer faces is fuel. If we want to send a spacecraft to another star, we cannot use rocket fuel. It is simply too heavy. To carry enough fuel to get there, you would need a ship the size of a moon, which is impossible to build. The best solution, according to physics, is to leave the fuel behind. We would build a light sail. This is a spacecraft that uses the pressure of light either from the sun or from giant lasers on Earth to push it forward just as wind pushes a sailboat on the ocean. However, a light sail has specific design constraints. To catch enough light to move fast, the sail must be incredibly thin, perhaps only a few millimeters thick, but it must also be very wide. It needs to be extremely lightweight but strong enough not to tear. This brings us to the sheet. If you have a giant ultra-thin sheet of material floating in space, how do you keep it from crumpling up like a piece of waste paper? You cannot use heavy metal beams to hold it open, because that adds too much weight. The engineer's solution is simple rotation, gyroscopic stabilization, the art of the spin. Think about a bicycle. When the bicycle is standing still, it falls over easily. But when the wheels are spinning, it becomes stable. It wants to stay upright. This is a physical principle called gyroscopic stabilization. A spinning object resists being pushed off its path. If we build a light sail, we would likely spin it to keep it flat and stable. By spinning, the craft's centrifugal force pulls the material outward, keeping the sail tight and rigid without needing heavy support structures. Now look at Oumuamua again. The data told us it was a strange, elongated object tumbling through space. While astronomers saw a weird rock, an engineer sees a potential light sail that keeps its structure through rotation. The tumbling motion of Oumuamua might not be a loss of control. It could be the result of a long journey where the specific equipment meant to dampen the spin has shut down, or perhaps the tumbling is intentional to scan signals from all directions. If Oumuamua was a flat, thin object like a pancake that was tumbling, the light from the sun would reflect off it in a very specific way. Bright when the flat side faces us, and dark when the thin edge faces us. This matches the extreme brightness changes astronomers observed. The cigar shape might have been an optical illusion caused by a flat disk spinning at a high angle. To an engineer, the rotation is not a mystery, it is a necessity for survival. The art of cosmic camouflage. The second major challenge for our interstellar probe is survival. Space is not empty. It is filled with dust radiation and micrometeoroids. Furthermore, if we are sending a probe to a civilization that might be paranoid or hostile, do we want them to know we are watching? If we send a shiny metallic sphere that beeps loudly, it might be shot down or captured. A smart engineer might design the probe to use camouflage. How do you hide in space? You dress up as the locals. In the vastness of space, the most common objects are rocks and comets. If we wanted to send a surveillance probe to another solar system, we might coat the exterior with dull, natural-looking material. We would make it look like an asteroid. This protects the delicate electronics inside from micrometeoroid impacts like a shield, and it makes the object appear boring to any observers. This leads us to the comet theory. The prompt asks us to consider camouflage in the form of a comet. This is a brilliant engineering strategy. Recall that Oumuamua accelerated as it left the sun moving faster than gravity alone allows. In nature, comets do this because heat melts their ice, creating jets of gas that act like rocket thrusters. But Oumuamua had no visible tail. It looked like a rock, but moved like a comet. If we were designing the stealth probe, we might use this exact mechanism. Perhaps the ship vents waste heat or gas to adjust its course, but it does so in a way that is invisible to telescopes. Or perhaps the surface is made of hydrogen ice, a material that turns to gas without leaving a visible dust trail. By designing a ship that mimics the physics of a comet, non-gravitational acceleration, but lacks the visual signature no tail, we achieve two things. We get a free boost of speed from the sun. We confuse the observers. They will argue over whether it is a rock or a comet, never realizing it is a machine, the perfect design. When we combine these elements, the blueprint becomes clear. We are not building a generic rocket, we are building a probe that is extremely thin to ride the light of stars. Because it is thin, it must spin to remain stable, utilizing gyroscopic forces to keep its shape. To survive the millions of years of travel and to avoid detection, we disguise it as a dark, reddish, tumbling, inert object, something that looks like a piece of space junk or a dead comet. From this perspective, the anomalies of Oumuamua stop looking like random weirdness. The high speed, the extreme aspect ratio, very long or very flat, the spinning and the mysterious push away from the sun are exactly the features we would write into the design specifications of our own interstellar probe. If nature did not build Oumuamua, then a civilization with engineers very much like our own did. They understood the physics of light, the stability of rotation, and the value of hiding in plain sight. The blueprint of Oumuamua is eerily similar to the blueprint we are currently drawing for our own future. To understand what Oumuamua was made of, we did not need to touch it. We did not need to land a probe on its surface or chip away a piece of its skin. In astronomy, light is the only messenger we need. By catching the faint dying photons that bounced off the object's surface, scientists could perform a kind of distant alchemy. They could break that light apart into a rainbow of colours, a spectrum, and read the chemical fingerprint hidden within. When astronomers looked at the light coming from this interstellar visitor, they expected the familiar signature of a comet. Comets are essentially dirty snowballs, remnants from the frozen edges of a solar system. They are packed with water ice, carbon dioxide, and dust. When they get close to a star, that ice warms up and turns into gas or creating a massive glowing cloud known as a coma. But Oumuamua refused to follow Fee's script. The first thing the light told us was about the colour. The object was not grey like a rock from the moon, nor was it bright white like fresh snow. It was red, deeply darkly red. In our own solar system, this specific shade of dark red usually tells a story of age and violence. It appears on objects that have been floating in the deep freeze of space for millions or billions of years, bombarded by high-energy cosmic rays. This radiation cooks the carbon-rich ices on the surface, slowly turning them into a sticky, tar-like organic goo, known as tholins. So at first glance, the chemistry seemed normal for an ancient object. It looked like a comet that had developed a thick red crust over eons of travel. But as scientists peeled back the layers of the data, the story got stranger. They went hunting for water. If Oumuamua was accelerating, pushing itself away from the sun, it had to be ejecting gas to create that thrust. The most common fuel for comets is water. The Spitzer Space Telescope, one of the most sensitive heat-seeking eyes humanity has ever built, turned its gaze toward the object. It searched for the infrared glow of water molecules or carbon dioxide gas escaping into space. It found nothing. The data was stark. There was no cloud of gas, there was no dust coma. The limits set by the telescope were incredibly tight. If Oumuamua was releasing water, it was releasing so little that it defied the laws of physics for an object moving that fast. It was drier than the driest desert on Earth. It appeared to be carbon depleted, meaning it lacked the usual carbon dioxide clouds we expect from comets. This chemical sequence was deafening. How could something move like a rocket but look like a dead stone? This is where the spectral data offered a fascinating alternative possibility, one that shifts the image from a dirty snowball to something far more rigid. When analysing how the object reflected sunlight, the data was consistent with two main possibilities. One was organic-rich rock, the other was metal, specifically a composition rich in nickel and iron. This brings us to one of the most evocative images to emerge from the study of Oumuamua. Imagine a shiny stainless steel knife floating in the void. If you were to toss that knife into the deep ocean of interstellar space and leave it there for 1 billion years, it would not stay shiny. It would be bombarded by the same cosmic radiation that hits comets. Over eons, a layer of interstellar gunk dust and simple organic molecules would bake onto the surface of the metal. To a telescope, this object would look like a dark red rock. The rust of the universe would hide the truth, but underneath that thin-baked coating, the core would remain solid metal. This stainless steel knife theory solves a major problem that the chemical analysis highlighted: structural integrity. We know Oumuamua was tumbling violently, spinning end over end every 7 to 8 hours. We also suspect it was incredibly long and thin, shaped like a cigar or a pancake. If it were a rubble pile, a loose collection of gravel and ice held together by weak gravity like many comets, the force of that spin should have torn it apart. it would have disintegrated into a cloud of dust. But it didn't, it stayed in one piece. This suggests that whatever chemical bonds held Oumuamua together, they were strong. The material had to be dense. A core of iron and nickel masked by a red organic skin fits the data perfectly. It explains the colour and it explains why it didn't shatter under the stress of its own rotation. However, the metal theory brings us back to the mystery of the gas. Metal does not outgas. A block of iron does not shoot jets of steam to push itself forward. So we are left with a paradox of chemistry. If it was made of ice and carbon dioxide, we should have seen the dust coma and the chemical signature of water, but we saw neither. The dust production was surprisingly low, almost non-existent. In a standard comet, for every kilogram of gas released, there is usually a lot of dust carried out with it. Oumuamua was incredibly clean. It was a ghost passing through the dark, leaving no footprints behind. On the other hand, if it was made of nickel and iron, which fits the reflection data and the structural strength, it should not have accelerated. A rock or a metal bar should simply follow the path of gravity, yet it moved as if it were being pushed. The alchemy of starlight left astronomers with a puzzle of missing pieces. The chemicals that should have been there, water, carbon dioxide, dust, were missing. The chemicals that appeared to be there, metals, organic crusts, contradicted the movement of the object. It was an object that looked like an asteroid, dry, rocky and metallic, but behaved like a comet. It was a hybrid that nature does not usually produce. The light reflected off Oumuamua told us that it was old, it was red, and it was likely rich in metals usually found in the cores of planets. But the silence where the water should have been remains the most significant chemical clue of all. It forces us to ask if it wasn't burning ice to move what was it using. As we pull back from the thrill of discovery and the rush of potential contact, it is vital that we pause. We must take a moment to ground ourselves in the cold, hard reality of observation. In the pursuit of science, particularly astronomy, the greatest enemy is often not the lack of data, but the story we tell ourselves about that data. We must confront the limitations of our own senses and the deceptive nature of light itself. This brings us to the concept of optical illusions and the absolute necessity of skepticism. To understand the universe, we rely almost entirely on light. We catch photons that have travelled for millions or billions of years across the vacuum of space. We assume that what we see is what is there. However, nature is a master of disguise, and physics can play tricks on us that are both beautiful and disorienting. Our eyes and even our most advanced telescopes are susceptible to illusions. Consider for a moment how easily we are fooled right here on Earth. When you look at a straw in a glass of water, it appears broken or bent at the surface. The straw has not changed, the path of the light has. This is a simple refraction. Now imagine this effect amplified on a galactic scale. In the vastness of the cosmos, gravity itself acts as a lens. This phenomenon, predicted by Einstein, occurs when a massive object like a cluster of galaxies sits between us and a distant light source. The gravity of that cluster is so strong that it bends the fabric of space. The light from the distinct object has to follow this curved path to reach us. The result is a gravitational lens. When we look through our telescopes, we might see a single galaxy appearing as 4 separate bright spots arranged in a cross or stretched out into a long curved arc known as an Einstein ring. If we were not careful, if we were not rigorous in our mathematics, we might believe we were seeing multiple galaxies or strange curved structures. In reality, we are seeing a mirage, a ghost of a single object distorted by the sheer weight of gravity. The universe is effectively a hall of mirrors reflecting and bending images, challenging us to discern the true shape of reality. We must also consider the famous case of Tabby's star. This is a perfect example of why we must temper our excitement with patience. A few years ago, astronomers observed a star formerly known as KAC 8462852. The data from this star was baffling. Most stars dim slightly when a planet passes in front of them, usually blocking just 1% or less of the light. But Tabby's star was dimming erratically, sometimes losing up to 22% of its brightness. The dips in light were not regular, they were chaotic and deep. The scientific community was stumped. The data did not fit the models of planetary orbits. In the absence of a simple explanation, the human imagination took over. The internet and even some scientists began to whisper about alien megastructures. People speculated that perhaps a massive civilization was building a Dyson sphere, a giant shell around their star to harvest its energy, and we were seeing the shadows of the construction panels. It was a thrilling idea. It sparked wonder and excitement across the globe. However, science demands that we rule out the natural before we claim the artificial. We had to calm our hearts and look again with colder, more objective eyes. After years of study and analysing the light in different spectrums, the answer turned out to be much more mundane. It was likely just dust. Fine, uneven clouds of cosmic dust were blocking the light. The alien megastructure was nothing more than a dirty window. This event serves as a humbling reminder: just because something looks engineered or impossible, it does not mean it is. Nature is capable of creating chaos that mimics complexity. Furthermore, we must discuss the properties of light that our eyes simply cannot see without aid, such as polarization. Light behaves like a wave. Usually these waves vibrate in all different directions, but when light reflects off a surface or passes through magnetic fields, it becomes polarized, vibrating in a single plane. To the naked human eye, polarized light looks exactly the same as normal light. We are blind to this hidden information. We could be looking at a star and miss entirely the massive magnetic fields swirling around it because our biology is not equipped to detect them. We require filters and instruments to reveal these hidden layers of reality. It reminds us that our perception of the world is incomplete. We are only seeing a thin slice of the whole picture. This leads us to a profound realization about our place in the cosmos. There is a danger in anthropomorphism, the tendency to project human qualities onto non-human things. We look at the face on Mars and see a monument only to find later it is just a hill with shadows. We see a rhythmic signal and think language, when it might be the rapid spin of a neutron star. Our brains are pattern-seeking machines evolved to spot predators in the grass, not to analyze astrophysical anomalies light years away. Therefore, the discipline of astronomy requires a deep, abiding humility. We must be willing to be wrong. We must be willing to let go of the exciting theory if the data leads us to a boring conclusion. We must accept that the universe does not care if we find it interesting. It only exists as it is. When we look up, we are not looking at a stage built for our entertainment. We are looking into a deep, complex void that distorts, bends, and hides its secrets. Every time we think we have found something that breaks the laws of physics, or something that proves we are not alone, we must take a breath. We must check our lenses. We must account for the dust. We must calculate the gravity. True scientific beauty is not found in the fantasy of what we want to see, but in the rigorous uncovering of what actually is. By stripping away our illusions, by admitting our potential for error, we do not diminish the wonder of the universe. Instead, we make our understanding of it more solid, more real, and ultimately more meaningful. We stand before the cosmos not as masters, but as humble observers, constantly wiping the fog from our glasses, hoping to see just a little bit clearer. On October the 3rd, 2025, the silence of the red planet was broken not by sound, but by a spectacular visual event. For billions of years, Mars has been a lonely wanderer, accompanied only by its two small potato-shaped moons, Phobos and Deimos. But on this day, the planet played host to a visitor from the deepest reaches of space. Comet 3I Atlas did not just pass by, it skimmed the upper edges of the Martian atmosphere in a gravity-defying dance that captivated the eyes of humanity looking through the lenses of our robotic envoys. The event began long before the visual spectacle reached its peak. High above the rusty surface, the European Space Agency's veteran orbiter Mars Express was the first to sense the intruder. Having circled Mars for over 2 decades, this machine was old but reliable. Its sensors, usually trained on the dry riverbeds and ice caps below, were now turned outward toward the black void. As the comet approached, travelling at a speed of tens of kilometers per second, Mars Express detected a shift in the environment. The comet was shedding tons of water vapor and dust every moment. These particles, invisible to the naked eye, slammed into the thin magnetic environment of Mars, creating an ultraviolet glow that only the machines could see. The distance between the comet and Mars was incredibly short in astronomical terms. It passed within 50,000 kilometers of the planet's surface. To put that in perspective, that is much closer than our own moon is to Earth. At this close range, the gravity of Mars pulled gently on the comet, slightly altering its path, while the comet's coma, the fuzzy cloud of gas surrounding its core, brushed against the top layer of the Martian atmosphere. It was a cosmic handshake, a brief mixing of materials from the frozen outer solar system with the dusty atmosphere of the inner solar system. Down on the surface, the view was even more breathtaking. In the Jezero crater, the NASA rover Perseverance woke up from its sleep mode. The sun had set hours ago, and the temperature had dropped to minus 80 degrees Celsius. Under the dark pinkish-black sky, the rover's neck craned upward. Its primary camera system, known as Mastcam-Z, was programmed with precise coordinates sent from Earth nearly 15 minutes earlier. Because of the vast distance between Earth and Mars, real-time control was impossible. The rover was on its own, acting as a robotic photographer waiting for a celebrity to walk the red carpet. Through the thin dusty haze of the Martian night, a new star appeared. Unlike the sharp, steady points of light from distant stars, this one was fuzzy and elongated. As the camera shutter clicked open for a long exposure shot, it captured the streak of the comet cutting across the constellations. From the surface of Mars, the comet looked massive, brighter than Venus appears from Earth. Its tail stretched across a significant portion of the sky, glowing with a ghostly blue-white light that contrasted sharply with the eternal red dust of the ground. This moment represented a triumph of international cooperation. It was not just an American or European event, it was a global orchestra of science. While Perseverance watched from the ground and Mars Express watched from above, other spacecraft joined the observation network. The ExoMars Trace gas orbiter adjusted its trajectory to sniff the molecules the comet left behind. The Hope probe sent by the United Arab Emirates pulled back to a higher orbit to capture a wide-angle picture of the entire planet with the further comet in the background. The Chinese Tianwen orbiter focused its high-resolution cameras to look for any fragmentation in the comet's nucleus. For a few hours, every operational machine at Mars turned its attention away from the red dirt and toward the visitor. The data they collected was effectively a treasure chest for scientists. They were looking for simple ingredients: water, carbon dioxide, and carbon monoxide. By reading the chemical fingerprint of the comet as it interacted with Mars, scientists back on Earth hoped to understand if comets like this one could have delivered water to Mars billions of years ago, back when the planet was warm and wet. The visual beauty of the encounter was profound. Images that were beamed back to Earth hours later showed a scene that looked like science fiction art. One particularly striking photo from the Hope probe showed the crescent edge of Mars lit by the distant sun, with the bright icy head of 3I Atlas rising above the horizon. The blue ion tail of the comet pointed directly away from the sun, looking like a straight laser beam, while the heavier dust tail curved gently, creating a fan shape against the stars. As the closest approach ended, the comet began to pull away, using the gravity of Mars to gain a little extra speed for its journey toward the sun. The event was silent and peaceful, but the dynamics were violent. The solar wind, a stream of charged particles from the sun, was battering the comet, stripping away ions and creating a turbulent wake. Mars, with its patchy magnetic umbrellas, added to the complexity, twisting the comet's tail into strange knotted shapes for a brief time. For the team on Earth, the success was a relief. There was always a fear that the dust from the comet could damage the orbiters, hitting them like microscopic bullets, but the calculations held true. The spacecraft remained safe, observing the spectacle from a respectful distance. As 3I Atlas faded into the Martian dawn, becoming just another bright dot in the sky, it left behind a changed planet. The upper atmosphere of Mars was now rich with hydrogen and oxygen from the comet's water ice. The rovers went back to drilling rocks, and the orbiters returned to mapping the surface. But for a brief moment, the eyes of humanity had been stationed on a different world, looking up at the same sky we see from Earth, watching the same traveller. It was a reminder that in the vastness of the solar system, all planets are connected by the wandering gravity of the sun and the visitors that pass between them. The comet was now hurtling inward, destined to grow even brighter and hotter, but its encounter with the red planet would remain one of the most visually stunning chapters of its long journey. For centuries, humanity looked up at the night sky and imagined our solar system as a lonely island in a vast dark ocean. We believed that the sun, the planets, the moons, and the asteroids were a closed family moving together in a predictable dance. We thought that anything outside of this family was too far away to ever reach us. We were comfortable in our isolation. But in the last decade, that illusion of solitude has been shattered. The ocean is not empty. It is full of drifters, wanderers, and travellers. We have realised that our solar system is more like a busy train station than a lonely island. To truly understand the significance of our new guest 3I Atlas, we must look back at the two travellers that came before it. We must tell the tale of the three visitors who changed how we see the universe. The story begins in October of 2017. That was the year the first visitor arrived. We named it Oumuamua, a Hawaiian word that roughly translates to a messenger from afar arriving first. Oumuamua was a shock to the scientific world. It did not behave like anything we had ever seen before. When astronomers looked at it through their telescopes, they expected to see a comet. Comets are common in our own solar system. They are balls of ice and dust that melt when they get close to the sun, creating a long, beautiful tail. But Oumuamua had no tail. It was completely dry. It was not a round ball, but shaped strangely like a long cigar or a flat pancake tumbling end over end through the dark. It was dark red, likely stained by millions of years of radiation from cosmic rays. But the strangest part was how it moved. As it left our solar system, it sped up. Something was pushing it, but without a tail of gas to act like a rocket engine, scientists were confused. Was it a piece of alien technology? Was it a chunk of hydrogen ice? To this day, Oumuamua remains the mysterious stranger, the weird visitor that defied all our rules. It left us with more questions than answers. 2 years later, in August of 2019, the second traveller arrived. This one was discovered by an amateur astronomer named Gennady Borisov, and so it was named 2N Borisov. If Oumuamua was the mysterious stranger, Borisov was the familiar cousin. As soon as telescopes pointed at it, astronomers breathed a sigh of relief. It looked exactly like the comets we have in our own solar system. It was a dirty snowball. As it got close to the heat of the sun, it began to release gas and dust. We saw water vapour. We saw carbon monoxide. We analysed its chemistry and realised it was almost identical to the comets formed in our own backyard. Borisov was important because it was normal. It proved that other stars have systems just like ours. It told us that the recipe for making planets and comets is likely the same all across the galaxy. It was a comforting confirmation that we are not unique freaks of nature. The universe makes sense. Now we stand before the third traveller, 3I Atlas. If Oumuamua was the confusing anomaly, and Borisov was the standard model, 3I Atlas, sits right on the boundary line between them. It is the bridge that connects the strange to the familiar. When we study 3I Atlas, we do not see a perfect typical comet, but we also do not see a confusing dry rock. We see something in the middle. It has a faint coma, a cloud of dust surrounding it, which tells us it contains some volatile ice, perhaps nitrogen or carbon monoxide frozen deep within its core. However, it is not releasing huge rivers of gas like Borisov. It is old, tired and weathered. 3I Atlas helps us understand the diversity of the galaxy. Imagine walking through a forest. Oumuamua was like finding a piece of twisted metal, strange and hard to identify. Borisov was like finding a pine cone, exactly what you expect to find in a forest. 3I Atlas is like finding a stone covered in unique moss. It is natural, but it tells a specific story about where it came from. It suggests that the space between stars is filled with a massive variety of objects. Some are rocky fragments from planets that were destroyed, some are icy leftovers from the birth of stars, some are dark burnt-out husks that have travelled for billions of years. The arrival of 3I Atlas changes the narrative from a freak event to a population. In science, 1 data point is an accident, 2 data points are a coincidence, but 3 data points, that is a trend, that is a pattern. The existence of this family of 3 objects implies that there are trillions more out there. At any given moment, there are likely thousands of interstellar objects passing inside the orbit of Mars, just too small or too dark for us to see. We are currently swimming through a river of these objects. 3I Atlas teaches us that our solar system is constantly exchanging material with the rest of the galaxy. This concept is profound. It suggests a theory called panspermia might be possible. This is the idea that the ingredients for life water, carbon organic molecules, could be carried from one star system to another on the backs of these travellers. Borisov brought water. Oumuamua brought organic compounds. 3I Atlas brings complex dust. They are like cargo ships carrying the building blocks of the universe from port to port. Comparing 3I Atlas to its predecessors also highlights how much our technology has improved. We found Oumuamua only after it had already passed the closest point to Earth and was running away. We found Borisov on its way in, but with 3I Atlas, we have been tracking it with better understanding, using what we learned from the first 2 to extract every ounce of data. We are no longer surprised children, we are becoming experienced observers. So as 3I Atlas continues its journey across our sky, moving at speeds of tens of thousands of kilometers per hour, we should not look at it as just another rock. We should look at it as a member of a diverse family. Oumuamua taught us to expect the unexpected. Borisov taught us that the laws of physics are universal, and now 3I Atlas teaches us about the complexity and richness of the galaxy. The universe is not a series of isolated, lonely bubbles. It is a bustling, crowded highway with history and chemistry flowing freely between the stars. We used to think we were alone in a dark room, Now we know the room is full of visitors. We just needed to turn on the lights to see them. 3i Atlas is simply the latest traveller to step into the light, reminding us that the story of our solar system is just one small chapter in a much larger, more connected book. It was the middle of the night, or perhaps the early morning. In the bunker, time was a blur measured only by the hum of the servers and the rhythmic cycling of the air filtration systems. We were exhausted. Our eyes were red, our coffee cups were empty, and our patience was wearing thin. This is the state of mind where mistakes happen not because we lack intelligence, but because we are desperate for hope. This brings us to the story of Tiago and the incident that we now call the Silicon Mirage. Tiago was one of our brightest data analysts. He was young, eager, and he trusted the artificial intelligence implicitly. For him, the AI was not just a tool, it was a partner, a superior mind that could see patterns invisible to the human eye. We were working on a critical problem regarding the soil regeneration project. We needed a specific enzyme that could break down the toxins in the scorched earth outside, but every natural combination we tested had failed. The process was slow, painful, and discouraging. Then Tiago turned to the central AI model. He fed it decades of botanical data, chemical structures, and soil composition reports. He asked the machine to hallucinate a solution to dream up a molecular structure that did not exist in nature but could theoretically work. At 03 hours, Tiago stood up his chair, scraping loudly against the floor. "I have found it," he whispered. Then he shouted, "I have found it, the AI solved it." We gathered around his screen, there it was. A beautiful complex molecular structure displayed in glowing blue lines. According to the simulation, this compound would not only neutralize the toxins, but would do so with 99% efficiency. It was a miracle. The AI had run millions of simulations in seconds and delivered the golden key we had been searching for. The room exploded with relief. People were hugging. Tiago looked like a hero. For the first time in months, the heavy weight of impending doom lifted off our shoulders. We felt light. We felt saved. But this is where the danger lies. We fell into the trap of the AI mirage. Like a traveller dying of thirst in the desert who sees there's a shimmering lake on the horizon, we saw exactly what we wanted to see. We were so desperate for a solution that we forgot the most basic rule of science skepticism. We rushed to synthesize the compound. We skipped the peer review protocols because after all, the machine is smarter than us, right? The machine does not make math errors. The machine does not get tired. We spent 3 days of our precious resources creating this miracle enzyme. We poured our energy, our rare chemical stocks, and our emotional sanity into it. When the physical test finally happened, the atmosphere was electric. We placed the synthesized compound onto a sample of toxic soil in the sealed chamber. We waited for the reaction. We waited for the toxins to break down. Nothing happened. We waited an hour. The sensors showed zero change. The toxins remained. "Maybe the dosage is wrong," Tiago said, his voice trembling. We doubled the dose. Still nothing. Then our lead chemist Sarah stepped forward. She had been quiet during the celebration, the only one who looked doubtful. She pulled up the AI's data logs and began to trace the logic the machine had used. She worked backward, step by step, dismantling the digital dream. 2 hours later, she turned to us. Her face was not angry, but sad. "It is a hallucination," she said softly. The AI connected 2 databases that should never have been mixed. It took the structure of a completely unrelated plastic polymer and combined it with a plant protein because the shapes look similar in the geometry engine. Chemically, this thing is useless. It is just inert sludge. It looks perfect on a screen, but it has no reality. The silence in the room was heavier than the air outside. Tiago slumped into his chair, devastated. He felt he had failed us. But the truth was, we had all failed ourselves. This incident taught us a profound philosophical lesson about the difference between information and truth. In the modern age, we are obsessed with speed. We want instant answers. We treat technology like a god that can bypass the hard work of understanding. We assume that because a computer processes data faster than a human brain, it must be right. But AI does not understand the world. It only understands probability and patterns. It predicts the next word in a sentence or the next shape in a sequence. It does not know what a toxin actually feels like or what survival means. It just plays a game of math. The danger is not that the machine lies to us maliciously. The danger is that the machine is a mirror. It reflects our own desires back to us. We wanted a miracle, so when the AI offered a nonsensical pattern that looked like a miracle, we accepted it without question. We projected our hope onto the screen. We learned that day that verification is a form of discipline. Science is not meant to be fast. Real discovery is slow. It is boring. It involves checking the same number 100 times. It involves staring at a petri dish for weeks waiting for a tiny change. It is a process of elimination of proving yourself wrong over and over again until the only thing left is the truth. We had tried to shortcut that process. We tried to cheat the universe by using a supercomputer to skip the struggle. But nature cannot be cheated. After the Tiago incident, we changed our protocols. We still use AI, of course. It is a powerful tool for sorting data, but we no longer treat it as an oracle. If the AI suggests a solution, we treat it as a rumor, not a fact. We assume it is wrong until we can prove it right with our own hands in the physical world. Tiago recovered eventually. He became one of our most careful researchers. He learned that data on a screen is just a ghost. Real truth is something you can touch, something that stands up to the harsh light of reality. This is the struggle of our species. We create tools to extend our reach, but often those tools blind us. We confuse the map with the territory. We confuse the simulation with the life. As we move forward trying to heal this broken planet, we must remember that technology can calculate the path, but only human judgment can walk it. We must be patient. We must be slow. Because in a world full of digital illusions, the only thing that will save us is the hard, unglamorous, and undeniable truth. For thousands of years, humanity looked up at the night sky with a mixture of wonder and terror. A comet appearing in the heavens was often seen as a bad omen, a message from the gods predicting war, famine, or the death of a king. We were helpless, standing in the dark, waiting for whatever the universe decided to throw at us. But that era has ended. We have entered a new phase of our existence. We have begun what scientists call the long watch. This is not a passive wait. It is an active, determined effort to map the darkness and understand our neighbourhood in the solar system. The long watch is our commitment to future generations that we will keep our eyes open. To do this, we are building machines of incredible power and sophistication, tools that act as the eyes and ears of our planet. The first of these great sentinels is the James Webb Space Telescope. While many people know it for its beautiful pictures of distant galaxies, it is also a vital tool for planetary defense. Unlike our eyes, which see visible light, the James Webb sees an infrared. This is crucial because many of the most dangerous objects in space are dark. They are cold rocks floating in the void, reflecting very little sunlight. Against the black background of space, they are almost invisible to traditional telescopes. However, even a cold rock has a tiny amount of heat and it glows faintly in infrared light. The James Webb is so sensitive that it can detect this faint heat from millions of kilometers away. It acts like a thermal camera for the solar system. When we discover a strange object like the interstellar visitor Oumuamua, we can turn this powerful eye toward it to learn what it is made of. Knowing if an object is a solid metal rock or a loose pile of dust and ice is essential. If we ever need to deflect one, that information will decide whether we succeed or fail. But the James Webb has a narrow field of view. It looks at small patches of the sky in great detail. To protect the Earth, we also need a wide view. We need to see everything at once. This is where the Virasi-Rubin Observatory comes in. Located high on a mountain in Chile, this telescope is currently preparing for a project called the Legacy Survey of Space and Time, or LSST. Think of the Rubin Observatory not as a camera that takes a single photo, but as a machine that makes a movie of the universe. It has a massive mirror over 8 meters wide and the largest digital camera ever built for astronomy. Every few nights it will scan the entire visible southern sky. Then it does it again and again. By comparing these images, computers can instantly spot anything that has moved. The stars remain still, but asteroids and comets will shift their position from one night to the next. The Rubin Observatory is expected to find millions of previously unknown objects in our solar system. It will increase the number of known asteroids by a factor of 10. It creates a live map of traffic in our solar system, ensuring that nothing can sneak up on us from the southern sky without triggering an alert. While telescopes watch, we are also learning to hunt. One of the most exciting developments in this field is a mission by the European Space Agency called the Comet Interceptor. In the past, if a new comet appeared from the deep freeze of the outer solar system, we had no time to prepare. These long-period comets travel incredibly fast. By the time we see them, it is usually too late to build a rocket and launch it to meet them. The Comet Interceptor changes the strategy completely. Instead of waiting for a target to appear and then launching, we will launch the spacecraft first and simply wait. These spacecraft will be parked in a stable point in space about 1.5 million kilometers from Earth, in a region where the gravity of the Earth and the Sun balance out. It will sit there patiently, perhaps for years. It is lying in wait like a spider in the web. The moment a new pristine comet from the edge of the solar system is discovered, perhaps by the Rubin Observatory, the comet interceptor will activate. Because it is already in space, it does not need to wait for a launch window. It will fire its engines and travel to intercept the comet as it rushes toward the Sun. When it gets close, the main spacecraft will separate into 3 smaller pieces. These 3 probes will fly around the comet from different angles, creating a 3-dimensional model of its shape, its dust, and its gas. This mission represents a shift in human thinking. We are no longer reacting to threats. We are anticipating them. We are pre-positioning our defenses before we even know what the target is. This brings us to the true heart of the long watch, the human spirit. Building these machines takes decades. The scientists who design a mission like the Comet Interceptor might be retired by the time it finally meets its target. The astronomers who advocated for the Rubin Observatory spent years in meetings and planning sessions long before the first piece of glass was polished for the mirrors. This requires a special kind of patience. It requires us to care about a future that we might not live to see. It is the modern equivalent of planting a mighty oak tree. We plant it not for our own shade, but for the shade it will provide to our grandchildren. The search for hazardous asteroids and comets is a tedious task. It involves sifting through terabytes of data, checking and rechecking calculations and tracking points of light that move fractions of a degree across the sky. It is not always exciting. It is the slow, steady work of cataloguing the heavens. But this persistence is what makes us a resilient species. We have moved from fear to curiosity, and from curiosity to responsibility. The Long Watch is a declaration that we intend to survive. It is a promise that we will not go the way of the dinosaurs simply because we were not looking up. As these new telescopes come online and these new missions launch, the map of our solar system fills in. The dark areas on the map are shrinking. The here-be dragons regions of space are being illuminated by data and analysis. With every new asteroid catalogued and every comet orbit calculated, the Earth becomes a slightly safer place. This vigilance is the price of survival in a chaotic universe, but it is a price we are now willing and able to pay. We are standing guard, watching the dark so that life on Earth can continue to thrive in the light. And now we have reached the end of our observation. The great journey, at least for us, is coming to a close. Take a deep breath in and let it out slowly. Let your shoulders drop away from your ears. Unclench your jaw. Let your hands rest gently. You are safe here. You are warm. You are ready to drift into the quiet. Imagine you are standing at the window of a spaceship watching that mysterious traveler move away. For the last hour, we have followed this strange object through the solar system. We watched it dive toward the sun, dancing dangerously close to the heat. We saw it tumble and turn, flashing its light like a lighthouse in the deep ocean of space. We marveled at its speed, moving at tens of thousands of miles every hour, faster than anything we could ever chase. And now we watch it leave. It is getting smaller now. The details we tried so hard to see are fading. The reddish hue, that colour of ancient rust and deep time, is blending into the blackness of the void. It is becoming a silhouette, then a dot, and soon it will be nothing more than a memory. As it fades, think about the mystery it leaves behind. We ask so many questions. Was it a rock born from the fiery collision of planets in a star system far away? Was it a shard of ice coated in dust that has been wandering between the stars for eons? Or was it something else? Was it a craft, a probe, or a solar sail built by hands? We will never shake created by minds we will never meet. The object does not answer. It keeps its secrets, and in a way that is a beautiful thing. It reminds us that the universe is not obligated to explain itself to us. It simply exists. There is a profound comfort in that realization. Sometimes we feel the need to know everything, to control everything, to have a label for every star and every stone. But this object teaches us to be comfortable with the unknown. It reminds us of the innocence of humanity. We are so young. In the timeline of the cosmos, which stretches back billions of years, we have only just opened our eyes. We are like children standing on the shore of a vast dark ocean, picking up a seashell and wondering where it came from. We do not need to know the answer tonight. The mystery is not a problem to be solved right now. It is a bedtime story to be enjoyed. Whether it was a natural wanderer or an artificial visitor, the message is the same. We are not the center of everything, but we are a part of something magnificent. We are small, yes, but we are not insignificant. We are the part of the universe that has learned to look up and wonder. Now watch as the object crosses the invisible line into the interstellar night. It is leaving the warmth of our sun. The light is growing dimmer. The sun, which is so bright and hot to us, is becoming just another star in the sky to this traveller. The temperature drops, the silence deepens. Space is often called silent, and we might think of silence as empty or lonely. But tonight, let us think of silence as peaceful. It is the absence of noise, the absence of rush, the absence of demands. In this silence, there are no phones ringing. There are no deadlines. There is no traffic. There is only the velvet smooth darkness stretching out forever. This darkness is not scary, it is soft. It is the colour of sleep. Think of the universe as a giant, comfortable room. The stars are like small nightlights plugged into the walls, glowing gently just enough to let you know you are not alone. The vast distances between the stars are just room for you to breathe, room for you to dream. Imagine you are floating alongside that object one last time. You are weightless. There is no gravity pulling you down, no heavy blankets, no tension in your back or your legs. You are simply drifting. You are moving forward with no effort at all. You are coasting on the momentum of the cosmos. The object is now so far away it is invisible. It has returned to the dark. It will travel for millions of years more. It will pass other suns. It might pass other worlds. It will witness nebulas glowing in pink and gold gas. It will fly through clouds of diamond dust. It will see things we cannot even imagine. But it does not worry about the journey. It does not worry about where it is going or when it will arrive. It just travels. It surrenders to the flow. You can do that too. You can surrender to the flow of sleep. You do not need to try. You do not need to force it. Like the object drifting through the vacuum, you can just let go. Let the current carry you. The universe is billion hours of years old. It has seen everything. It holds you now. You are made of the same stuff as that travelling stone. You are made of the same atoms as the stars. You belong to this night. You are at home in this quiet. The excitement of the discovery is over. The data has been collected. The telescopes are turning off. The lights in the observatory are dimming. The scientists are going home to their beds. The world is turning away from the sky and burying its head in the pillow. Everything is slowing down. The spinning of the object slows in your mind. The beating of your heart slows to a steady rhythmic drum. Your breathing is slow and deep like the tides of the ocean. In and out, in and out. The night is silent. The sky is deep. The stars are watching over you like guardians of the dark. Let the image of the traveller fade completely now. It is gone. It has entered the silent night. And now you follow it. Not into the cold of space, but into the warm, rich darkness of your own rest. There is nothing left to see. There is nothing left to solve. There is only the feeling of the bed beneath you and the blanket above you. You are a tiny, precious point of consciousness in a vast, gentle universe. Drift away now. Float into the mystery. The stars are singing a lullaby of light, but it is a silent song felt rather than heard. It is a song of peace. It is a song of rest. Good night to the traveller. Good night to the stars. Good night to the moon. And good night to you. Deep sleep, silence, peace.